How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at Chatliers principle. So our objectives will be to analyze what would happen to an equilibrium that is subjected to a disturbance, such as changes in temperature, pressure, volume, presence of a catalyst, etc. All right, so what is Chatliers principle? It's a principle stating that if a constraint, such as a change in pressure, temperature, or concentration of a reactant, is applied to a system in equilibrium, the equilibrium will shift so as to tend to counteract the effect of the constraint. So systems at equilibrium like to restore equilibrium. If you do something that's going to disturb that equilibrium, it's going to respond in such a way to restore that equilibrium. So some general rules. If a substance is added, the equilibrium shifts away from the side that has it. So if you add a product, it's going to shift towards the reactant side. If you add a reactant, it's going to shift towards the product side. Right? So we're trying to keep this KEQ equal. If I were to add some Y, it's going to shift towards the X side. All right, if I added more product, well, the equilibrium is going to respond so in a way that's going to restore that equilibrium. So it's going to have to use up some of those products to make more reactants. Right? So basically, if I were to add, let's say, a reactant, well, then I need to add more product. Second general rule, if a substance is removed, the equilibrium shifts to replace it. So if I remove a reactant, it's going to shift towards the reactants to replace them. And if I remove a product, I'm going to shift towards the product to replace them. So if I were to remove a reactant, hey, I need to replace that. So I'm going to have to remake some reactant, so I'm going to use up the products. Pressure. Pressure has its own rule. Increasing the pressure or decreasing the volume, which would increase the pressure, shifts in equilibrium toward the side that has fewer moles of gas. So if I'm taking a look at this example, on the left side we only have 1 mole of gas, and on the right side we have 2 moles of gas, and I have my KEQ right here. So decreasing the pressure or increasing the volume, which would decrease the pressure, shifts towards the side with the greater moles of gas. If you got less pressure, you got more room for those gases to spread out, so you're going to favor the side that's got more gas. If there's no gases, or both sides has an equal number of moles of gas, then there's no effect. It won't have any effect. And on the right side here, I'm showing it mathematically. Why does the pressure affect the equilibrium? Well, if I take a look, here, left side, 1 mole of gas, right side, 2 moles of gas, got my KEQ. So at equilibrium, I have these pressures for those things. So my KEQ expression is as follows. I plug in the number, I get my KEQ. But what happens when we double the pressure? Well, this 0.33 is going to become 0.66, and this 0.67 is going to become 1.34. And when I plug those values in, we get a different number. That's not equal to our KEQ. So our Q, which is this 0.325, is greater than KEQ, so it's going to shift towards the left because the left has the fewer number of moles of gas. Temperature. So changing the temperature changes the value of KEQ. So knowing the delta H for the process, you can write heat into the equilibrium and treat it like any other product or reactant. So if it's an endothermic process with a positive delta H, you write it as a reactant, right? Because it's absorbing that heat. The heat's going into the substances and being absorbed. If it's exothermic with a negative delta H, heat's being given off, so heat can be written as a product. And then you just treat it like you would anything else. Raising the temperature shifts away from the side that has the heat because it's like you're adding more heat, so it's going to shift away from the side that had the heat. If you decrease the temperature, it's like you're removing the heat, so it's going to shift towards the side that has the heat. So let's take a look at an example. So here I have an endothermic reaction. I got a positive delta H. So that tells me this heat has to go on the reactant side because it's being absorbed. So I rewrite it. Same equation, just with the heat written on the reactant side. So we said increasing the temperature for endothermic processes shifts it to the right. Basically, if we increase the temperature, we've added more heat, so it's going to shift away, right? If we add, we shift away. So if I add heat to this endothermic process, I'm going to end up making more products. If I were to decrease the temperature, that's the same thing as removing the heat. It's going to respond in the opposite way. So we got add, shift away. if we remove stuff, we shift to replace it. So if I'm decreasing the temperature and I'm removing heat, I'm going to have to shift in such a way to replace it. So I'm going to shift towards the left. And because of that, the KEQ is going to be a smaller value because we're messing with the temperature. Now, exothermic processes, same kind of process, same approach, same steps you're going to take. I see I got a negative delta H, so I know it's going to have to be a product. So I'm going to put heat on the product side because I'm giving that heat off. Now you do the same thing that you were doing. So if we increase the temperature, all right, well, that's like adding more heat. It's going to shift away from the side that we added to, so it's going to shift to the left. And because we're increasing the reactants, our KEQ is going to decrease. Remember, KEQ, it always has the products over the reactants. So if we're increasing the reactants, the value for KEQ is going to go down. And then the opposite, if I were to decrease the temperature, well, hey, I'm removing heat from my equilibrium. I got to shift to replace it. So that means, hey, I'm going to end up making more products, which is going to increase the KEQ because instead of, increasing the reactants, now we're increasing the number of products that we got, which is going to increase our KEQ. Remember, if you change temperature, you change the KEQ value. More general rules. Catalysts have no effect on the composition of the equilibrium mixture, but it will speed up reaching equilibrium. But the composition is unaffected. So you always are going to end up with the same proportion. It just, sometimes equilibrium will take a while to get there. So maybe you're trying to make a product and it's a really slow process. You can add a catalyst that's going to get it to equilibrium quicker, but you're going to make the same amount. So both forward and reverse processes are sped up. So if this is my potential energy diagram, right, I have a forward process, forward reaction. I also have a reverse reaction going in the opposite direction. What a catalyst does is it lowers that activation energy and it lessens the hump. It decreases the requirement for energy, so things happen quicker. But it does it for both the forward and the reverse process, so it's not going to affect where the balance is. At equilibrium, it's not going to affect the composition. It's just going to speed up getting there. And it's kind of like a seesaw. So I don't know if you were a kid ever. Chances are you probably were a kid. Maybe you played with a seesaw, right? So if I treated my double arrow like the fulcrum, that point where the things change, and I treated this like a seesaw, maybe you can visualize it a little bit easier. So what's going to happen if I want to keep this seesaw balanced? Well, if I add some more reactants, well, hey, now this side's going to be heavier. I have to shift things to the right so that it stays balanced, right? And then if I want to take a different approach, let's say I were to, oh no, I got rid of my seesaw. If I were to remove a reactant, well, hey, now this side's too light. I have to shift to replace that to keep the balance, right? That's going to be, true for most things. If I, add some NH3, well, hey, now this side's too heavy. I need to shift to make more stuff on the other side. There you go. But big things. Add, you shift away. And if you remove something, you have to replace it. All right, so here's an example. See if you can predict how would the equilibrium respond to the following stresses. So we have this equilibrium. We have a delta H written over here. It's a positive value. So what would happen if you increase the temperature? All right, well, if it's a positive delta H, that tells me that the heat is going to have to go on the reactant side. All right, if I increase the temperature, that's like adding a reactant, so it's going to have to shift to the right. If we add something, we got to shift away. Decreasing the pressure. All right, well, now I got to take a look at how many gases I got. I have 2 moles of gases on the left side, and I have 2 gases and 1 more gas, so I have 3 moles of gases on the right side. So if I decrease pressure, then it's going to shift towards the side with more gas. So it's going to shift to the right. Right? If we decrease the pressure, it's like making it more accommodating to have more gas because there's less pressure. so things can spread out more, you can have more gas. Adding a catalyst, no effect on the equilibrium. Removing of O2, well, let's see. I got O2 over here. If I remove it, I have to replace it, so I'm going to shift to the right. And if I were to add PCl3, well, let's see. I got PCl3, and I'm adding it. If I add, I have to shift away from that side, so it's going to shift to the left. There you go. All right, so summarize. Can you explain what would happen to an equilibrium that is subjected to changes in temperature, pressure, volume, presence of a catalyst, amounts of reactants or products? I hope so. All right, hope you found that helpful. Okay, bye.